friends upstairs, or I don't know, a heavy object. One of them gets fatigued and starts to apply erratic forces, stumbling and so forth. What can you do? Well, there are two solutions. One, you tell him, okay, just step aside, we'll do it without you. That's the weak link hypothesis. So you kind of kick the fatigue digit out of the system. The others are strong enough to do the task on their own accurately, so why bother? But there is another more sophisticated solution of the problem. You try to predict the erratic force changes of your poor partner who is fatigued, and you apply your own erratic changes out of phase so that overall the total force remains more or less steady. So we decided to check what actually happens. Here is the study. This person is sitting, pressing on 4 individual force sensors, and we asked people to produce 2 types of tasks. We call them discrete and rhythmic. So the discrete task is accurate ramp force production. It's always total force with what we show to our subjects, never forces of individual fingers. And the rhythmic task, there is a metronome at a comfortable rate, and 2 target zones, and we ask people just sit and bang, 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 produce force, drawing a sine wave on the screen. Then we fatigue the index finger. We selected the index finger for one good reason, that it's most independent. So it is least enslaved, and it shows least enslaving for other fingers. So when we fatigue it, other fingers are not really fatigued, because we fatigue it by exercise. We just ask people to press for certain time with the index finger, but other fingers also press because of enslaving. So to make sure that they are not fatigued, we selected the finger that's most independent. Okay, here is what happens. Now we ask our subjects to perform this task with the index finger and with all 4 fingers together, which is shown here as IMRL, index, middle, ring, little. Discrete task is reached. Well, you can see that during the discrete task, the subjects are much more accurate. It's not surprising because they have a template drawn on the screen to follow, while during rhythmic task, they're producing sine wave without the template. And you can see that when they perform it with the index finger task, subjects become less accurate. Well, that's what we expect. However, if you take a look at the 4-finger task, there is a trend for an increase in their root mean square error. But it's very, very small. It's actually not significant statistically even. So how come? Where does it come from? Well, the first somewhat surprising result that if in the 4-finger task you now look at the variance of individual fingers, force profiles, the index finger is the only one that performed the task. You can see that all fingers show on average an increase in their variance more or less to the same degree, although only one is fatigued. Okay, that's already a little bit unexpected, because if you fatigue one finger, why do other fingers show high variability, increased variability of their performance? Well, then when we looked at that variability and looked at what's going with the good and bad components, so variability variance within the uncontrolled manifold, well, null space of the Jacobian, with respect to total force production, and orthogonal to it. You can see that the good variability increased quite a bit, while the bad variability showed a tendency to increase, but not a lot. So if we put everything together, we usually use as an index of synergy the difference, normalized difference between the amount of good variability and the amount of bad variability. So when it's positive, this means that there is a synergy. When it's 0, when it's non-positive, there is no synergy stabilized. So you guessed right. You guessed wrong. I mean, there is no synergy stabilizing that variable. So when we computed it, we found out that yes, there is a significant increase in the index of synergy. So what does this mean? This means actually that the second strategy is being used between the 2 that I described for you before. So imagine now I'm going to use again 2-finger, although the experiment was with 4 fingers, but I cannot draw 4-dimensional things. So let's imagine that there are only 2 fingers. So on the left, before fatigue, there already was a synergy stabilizing total force. So the data distribution was mostly elongated along the good variability subspace. Now let's imagine that finger 1 is fatigued. So its variance is increased. It's a direct consequence of fatigue. You cannot do anything with that. What would have happened if finger 2 ignored it and kept its own old amount of variance? This is illustrated by the white ellipse on the right picture. The ellipse is tilted because the amount of variance of finger 2 is still small, the same as in the left picture, but variance of finger 1 is increased. If you project this tilted ellipse onto the bed subspace, it's going to be increased. So this means that variance of total force will go up. So if the other finger doesn't react and continues to perform at its own unfatigued amount of variance, this is not going to help. Variance of the total force will increase, and there is no way it can do otherwise. However, the only way to make sure that the ellipse is once again rotated along the direction of good variability is to increase the variance of the second finger and to co-vary the first and second finger stronger. And that's what we exactly observed in the experiment. So the system is smart enough to realize that there is this unusual way, or well, maybe not the first idea that comes to mind, how to deal in a multi-element system with an element that becomes noisy. Other elements also become noisy, and they co-vary negatively, very strongly. Then the total output of the system is not going to suffer, and well, that's the adaptation. We, by the way, also tried it using the so-called marginally redundant task. Now, marginally redundant task is the same as the previous one, but with only 2 fingers, and the platform with the force sensors is placed on a pivot in between the 2 fingers. So people have to produce force profile, and they have to keep the moment of force balanced. On the surface, it's a non-redundant task, because you have a force constraint, moment constraint, and you have only 2 elements. However, it's actually redundant because neither of the 2 constraints is absolute. You can have errors in total force and you can have errors in total moment. Not too large, but they're allowed. So as a result, we call this task still has an infinite number of solutions. So we call it marginally redundant. In this task, this picture shows again because there are only 2 fingers, this is an adequate illustration. For the in this task, stabilization of force and stabilization of moment compete with each other. Because to have stable force, you have to make sure that the 2 finger forces co-vary negatively. If one goes up, the other should go down. Then the total force doesn't suffer that much. However, if you want to stabilize total moment of force with the pivot in between, then if one force goes up, the other should also go up. They should co-vary positively, which is illustrated by these 2 ellipses that are orthogonal to each other. Obviously, you cannot have both. The system has to choose which one is more important. And by the way, with only 2 fingers, most subjects stabilize only moment of force and completely ignore force itself, although that's the explicit task. And then there is this small spot in the middle, surrounded by the yellow shade, which corresponds to more or less okay performance of both. So within that area, there is still a possibility to have a longer ellipse, a smaller ellipse, but it's all constrained. So when we ran the study there, the result was basically the same. That this is the index of synergy, and as you can see for the force production, this index is sometimes negative, particularly in this unstable condition with a pivot in between. It's negative, which means that total moment is stabilized and total force is destabilized by co-variation of individual finger forces. But if you take a look at the black bars as compared to white bars, obviously all black bars are more positive. They're either more positive or they even turn from negative into positive. So we have the same effect. When you fatigue one digit, the other digit increases its variability and it increases co-variation with the fatigue digit to make sure that the performance doesn't suffer too much. Okay, now this is the next object of study that we used is whole body multi-muscle action, and a few first kind of axiomatic statements. The brain doesn't use muscle-specific neural variables. People somehow guessed that since the end of the 19th century. Great Hewlings-Jackson, great British neurologist, once wrote that the brain knows nothing about muscles, it knows only movements. A very good statement. And the idea is that the brain unites muscles into groups, which is, by the way, done in this lab, one of types of the analysis, which people sometimes call synergies. But to us, this grouping of muscles together so that the activations scale in parallel, it's not a synergy, it's a chair. There are several with several legs. So there are several variables that scale together. For us, it doesn't qualify as a synergy. In order to qualify as a synergy, one has to formulate a hypothesis, synergy with respect to what, and perform an experiment and prove that it really exists or it doesn't exist. So we are going to call, I'm going to call them not synergies but modes, muscle modes. And for us, these are the higher order elemental variables. And then still the number of these variables is larger than the number of constraints. And these groups, muscle modes, are used to create task-specific synergies. So this is kind of a picture that we have in mind. For example, for a standing person, so the central nervous system manipulates 3 or 4 or 5, but relatively small number of variables, which then project with certain gains, K coefficients, on all the muscles we care to record. And since we're usually studying posture, then these are a whole bunch of abbreviations for leg muscles and trunk muscles, and they all lead to some kind of performance. Here I put a shift of the center of pressure, because during standing, shifts of the center of pressure is one of the common physical variables that are being studied. So the trick here is that all these things are non-observable. The only things we can record is muscle activations and shifts of the center of pressure, but we cannot record modes. So in order to define elemental variables in this study, we have to perform another experiment in anticipation of this main one. And okay. This is one of the examples how we do it. We ask a person to stand, look at the screen, and sway at a certain frequency in such a way that the center of pressure moves between two targets. It's a cyclic task. It's a very easy task to do. By the way, depending on the frequency, the movement pattern will look very different. If it's a slow movement, it's going to be rotation about the ankle joints. If the movement becomes fast, it's going to involve hip joints a lot. Surprisingly, the muscle modes, these groupings of muscle, are very consistent across all those frequencies. So this picture shows EMG time profiles for some selected muscles at a low frequency, 1/4 of hertz, to a very high frequency, 1.5 hertz. So the magnitude increases, but the general pattern is pretty similar. And then we do principal component analysis across multiple cycles, multiple measures. We do it with then rotation of the principal components and factor extraction. And we accept factors that account for a substantial amount of variance. And this is kind of a typical illustrative picture, what you can see as muscle groupings. So usually our groups, our muscle modes, they unite muscles of the dorsal part of the body together, ventral part of the body together, and muscles with lateral action separately. So in this picture it shows like tensor fascia lata, gluteus medius, and sometimes one of the other muscles get into that third mode. Sometimes there are 4 modes. Their composition is not that stable. I mean, it's stable across these relatively simple tasks. But if you put a person in unstable conditions, like balancing on an unstable board or on a slippery surface, then the composition of the modes changes quite dramatically. So we use a certain, criterion. The loading factors should be more than 0.5 and so forth, and we accept enough principal components so that no muscles are significantly loaded in further principal components. Then we stop. And then we also don't have the Jacobian, because muscle modes, just like EMGs, are measured in microvolt seconds. But we want to relate them to meters of displacement of the center of pressure. This is done with multiple regression techniques. So we look at shifts of muscle modes and corresponding shifts of the center of pressure, do multiple regression and get the coefficients. After we get those, we basically get the Jacobian for our system. So our elemental variables are muscle modes, their amplitudes. So these are vectors in the muscle activation space. These vectors, by the way, are quite stable, as this picture shows. I cannot draw anything multidimensional, but for example, if we, let's assume that E1, E2, E3 corresponds to everything else up to E12. So these are EMGs of individual muscles. And M1, M2, M3 are our vectors of modes. So these are eigenvectors of a length of 1. And these vectors are quite robust, which means that they are nearly parallel to each other within one number, and they are nearly orthogonal to each other with another number, between numbers of the vectors. And the Jacobian also is not dependent strongly on sway frequency. So if you simply then use the same data to see whether variations of the EMGs and corresponding variations in modes stabilize shift of the center of pressure, you'll find out that the answer is yes. So this left picture shows different frequencies from very slow to very fast, and magnitudes of good variance and bad variance. Also, they are normalized by dimensionality in each subspace. And the right picture shows the index of synergy. First of all, it's throughout positive, and as you can see, its magnitude doesn't really change consistently with the frequency. So surprisingly, although the movement looks very different, one is oscillation about the ankle joints, the other is oscillation about the hip joints, it's just the peripheral impression of the movement. But if you take a look at muscle activation patterns, the structure of muscle groupings and the way they covary with each other remains more or less invariant. All right, so what will happen with fatigue? To study that, we asked our subject to perform this exact task, so oscillating, looking at the feedback monitor, before and after fatigue of tibialis anterior. So again, we decided to fatigue a muscle that can be fatigued relatively independently of all other muscles. So the subject was seated and there was a load, and the subject did the dorsiflexion of the ankle joint and it was a timed dorsiflexion against a scaled load to the body weight of the subject until the subject couldn't do it anymore. And then the subject was placed again on the force platform and asked to perform the same task. All right, so we can skip that. This is a whole bunch of EMGs. The first three panels show the average integrated measures of EMGs at different frequencies, three different frequencies: before fatigue, which is black, and after fatigue, which is white bars. And as you can see in the first three bars, there is nothing special. It's not really much different from each other. Tibialis anterior, by the way, is the first muscle here, which is the fatigued muscle. The next three panels show variabilities of individual EMGs. And here the picture is very different. Although the absolute magnitudes of EMGs didn't change, their variability from trial to trial increased quite dramatically from cycle to cycle. And that's true not only for tibialis. In the tibialis, the first couple of columns, the white column is larger than the black one, but it's true for other muscles, like lateral gastrocnemius shows maybe even a bigger difference, but okay, it's also ankle joint. But rectus abdominis at the very end of this line, erector spinae, semitendinosus, tensor fasciae lata, all these muscles showed dramatically increased variability under fatigue, although they were definitely not fatigued in the experiment. So this suggests that the strategy that we observed in the fingers was also used here. Muscles that are not fatigued are increasing their variance in such a way that, well, we hope that performance doesn't suffer that badly. This is the same picture, but in the space of modes, or what's called sometimes synergies here. So mode is another EMG. It's kind of a macro EMG when many muscles are united together. Once again, this is variance, normalized variance for individual modes. Tibialis anterior is always in mode 1. And you can see, yes, it's increased. But mode 2, the variance is also increased. And mode 4, there are 4 that we accept, sometimes is also increased. So when we computed the two components of variance, good and bad. So in this picture, good variance, it's marked as VUCM and it's in black lines. And bad variance are shown for the 3 frequencies of action before and after fatigue. On top, before fatigue, well, you can see that variance UCM, the black line, is more or less, most of the time is above the gray line, which means that there is a synergy stabilizing center of pressure trajectory, as it should be, as we expected it to be. But if you take a look at the bottom picture, you can see that both variances went up quite significantly. However, the black line went up way more than the gray line. So most of the increase in variance under fatigue was channeled into this subspace of good variability. So this picture shows already the indices of synergies, and basically the result is the same, that under fatigue in multi-muscle tasks, not only the fatigued muscle increases its variability, but all other muscles do as well, but then they co-vary stronger their involvement in tasks across cycles in such a way that the center of pressure is relatively stabilized, the trajectory of the center of pressure. So what have we learned about the studies of fatigue? One is that there is a non-trivial adaptive strategy of the central nervous system to fatigue of individual elements, increase in variance of all elements, plus an increase in covariation, and it is used across tasks and systems, such dissimilar tasks as multi-finger force production and multi-muscle postural control. So since I'm already talking about postural control, I'm going to go into anticipatory control of posture. We all know that living beings behave in an anticipatory fashion. So even the spider doesn't go to where the fly is, but if the fly is crawling across the web, the spider goes to intercept the fly. And when we expect a postural perturbation, 2 things happen. One of them is relatively well known and studied, and I'm not sure that most of you know it. It's called anticipatory postural adjustment. So basically, if I'm standing like that and I'm making a fast movement, the mechanical coupling would throw my trunk backwards and there will be a perturbation to everything. I can fall down if I don't do anything. So when I do this movement and you record the activation of the muscles in throughout the body, you will see that the first signs of changes in muscle activation will be in the trunk muscles and leg muscles, not in the anterior deltoid muscle